All right. We have a test around November 22nd. After we go over the questions and answers for chapter 7 and 8, we will have a test. Okay. The final exam covers only 1 to 6. So 7 and 8 is not covered. 7 and 8 is covered by chapter 4. Now the topic of the chapter 8 is acids and bases. So we're going to learn about acid and bases and how to identify them and calculate pH, buffers, etc. Acids and bases are substances that react with each other to produce water. At the beginning, the basic acid bases react with each other to produce water and a salt. So there are so many types of acids and bases. One of them is Arrhenius acids and bases. They are proton and hydroxy bases, proton acid and hydroxy bases. And there's also Bronsted-Lowry bases, acids and bases. They don't have hydroxide ions. Bases are proton acceptors. Acids are proton donors. So we have to find a way to define strength of both Arrhenius acids, bases, or Bronsted-Lowry acids and bases. We're going to look into that, how we define which acid is stronger or which base is stronger. Now, among Bronsted-Lowry acid bases, in their reactions, you find conjugate acid-base pairs. We're going to define what conjugate means. So you will know what conjugate acid-base pairs in Bronsted-Lowry type acid-base equilibrium. The position of the equilibrium in a Bronsted-Lowry acid-base equilibrium is given by equilibrium constant. These acid equilibrium constants are called acid ionization constants. So these are related to equilibrium reaction that we discussed in chapter 7. And we're also going to look at properties of acids and bases and how it related to pure order, properties of pure order. When you add acid in the pure order, it has certain pH. So pH is a scale 0 to 14. 0 to 7 is being the acidic range, 7 being the neutral, 7 and up to 14 is a basic range, pH. We also have pOH. pH and pOH are basically mathematical concept of hydrogen ion concentration. P is a mathematical way of expressing hydrogen ion concentration, which is minus log hydrogen ion concentration. You take the log of hydrogen ion concentration and change the sign. Minus means change the sign. Then you get the pH. If you have OH ion concentration, you take the log of OH ion concentration, change the sign, minus log OH ion concentration, you get the pOH. We're going to do some examples. We use titration between acid and bases to calculate concentration of acid or the base that is required to neutralize certain amount of acid or base with specific molarity or concentration. Buffers are solutions made out of weak acids and its conjugate base, weak base or conjugate acid combinations that are used as buffers, means to retain the hydrogen ion concentration without being changed. Buffers can absorb certain changes in pH and maintain the pH. So buffers are important in biological systems. So we need to also calculate pH of a buffer solution. There are a few biochemical buffers like trees. We're going to talk about that. HAPs and how they affect the biochemical pH of biochemical solutions. The pH of blood is mainly affected by bicarbonate pH. Carbon dioxide dissolved in blood produce bicarbonate ion. So therefore, it acts as a buffer for blood pH. Again, we're going to identify acid and bases. When you see a formula, you can tell whether it's an Arrhenius acid or Arrhenius base, or Bronsted-Lowry acid or a base. You can write down equations for acid-base dissociation and identify the conjugate acid-base pairs. We're going to do that. Describe the role of solvent in acid-base reaction and explain meaning of pH. The acid base, when dissolved in water, changes the ionic equilibrium of water dissociation. Water dissociates into hydronium ions and now hydroxide ion. That is a equilibrium. It's a equilibrium, dissociation equilibrium that has a certain K value. It's called Kw, dissociation constant of water. When you add acid base to the water solution, that dissociation equilibrium is changed. So we're going to look into how it changed and how to predict the pH of the new solution. The pH, calculate pH from molarity data, concentration of hydronium ion or hydrogen ions. Calculate hydronium ion and hydroxide ion concentration from pH data. So we're going to be learning these things, how to do calculation. Provide examples of pH in chemical and biochemical systems. Describe the meaning and utility of neutralization reactions. That's the acid-base reaction. Utility is acids. If you spill, you need to neutralize with the base. What kind of bases could be used? So we're going to talk about that. State the meaning of buffer. Describe the application of buffers to the biochemical system, particularly blood chemistry. So buffers are an important part in acid-base chemistry, since they buffers maintain the same pH range, even when acid or base is added to the solution. buffers absorb the changes in pH and maintain it at the same level. Now let's talk about Arrhenius acid bases. They are the first acid bases that discovered long time ago. In 1884, Savante Arrhenius found out there are certain compounds in water behave as acid. They are sour taste. Acid have sour taste, and bases have slippery feeling to the touch. So we are not recommending anybody tasting acid or touching the bases. We have other ways now to find out whether something is acid or a base. To find something is acid or a base, you use a pH paper. The acid turns blue pH paper to a red color. Base turns red pH paper to a blue color. So therefore, you don't have to touch or taste acid bases to say which one is an acid or a base. Now, Arrhenius defined a substance that produces hydronium ion in water solution. When dissolved in hydronium in water, produce hydronium ion. Base as a substance that produces OH ion in an aqueous solution. That means acid increase hydronium ion concentration in water. Bases increase hydroxide ion in a water solution. Therefore, they change the dissociation equilibrium of water, hydronium ion and hydroxide ion, breaking up of water into hydronium ion and hydroxide ion. Therefore, the relative amount of OH and hydronium ion and OH are changed. Acid increase the amount of hydronium ion in the equilibrium, reduces the OH ion concentration to keep the equilibrium constant of acid dissociation from water dissociation, Kw, constant. Bases increase the OH ion concentration, decreasing the hydronium ion concentration. We're going to look into that. Acid is, according to Arrhenius, is substance that increase the hydronium ion concentration in water. Substance that increase the hydroxide ion concentration. If it is produced in the water solution, it increase the hydroxide ion concentration. The definition of an acid is a slight modification of original Arrhenius definition, which was he didn't know hydronium ion. He thought proton are in the aqueous solution. A proton cannot survive in a water solution. They combine with the water to produce hydronium ion. Therefore, when you're talking about a hydrogen ion protons in water solution, that you are basically talking about hydronium ion in the solution. Today we know hydrogen ion, hydrogen plus, which is a proton, react immediately with the water molecule to give hydronium ion. So that's the hydronium ion reaction. When you place an acid which contain protons, acid breaks up, protons in the acid breaks up and react with the water molecule to produce hydronium ion. For example, HCl is the Arrhenius acid. When dissolved in water, it reacts with water to give hydronium ion and chloride ion. The reaction is given below. HCl. Aqueous means dissolved in water. Water is liquid. So when they break up, hydronium ion and chloride ion are solvated by water, hydrated by water. This hydronium ion is aqueous, means in water solution surrounded by water molecules. Chloride aqueous means chloride ion surrounded by water molecules from the attraction between negative and positive parts of the water molecules. We use curved arrow to show the changes in position of electron pairs during the reactions. We use curved arrows to indicate resonance structures. Similarly, we can use arrows to show formation of OH bond and show the breaking of a HCl bond. OH bond between water is formed to produce hydronium ion. Chloride ion is removed. So the water electron pairs, that's the negative end of the water, is on oxygen. Dipoles are. Oxygen has negative dipoles. Then hydrogen has positive dipole, delta plus, delta negative. So delta negative on oxygen approaches the protons and pushes away the electron pair on the HCl bond. That's a bond breaking. And hydronium ion is formed and chloride ion is formed. Both get solvated, hydrated in water, as in the first equation. That's how acid works in water solution to increase hydronium ion concentration. The water with bases situation is slightly different. Iron and bases mainly have hydroxide groups or hydroxy bases. They are called hydroxy bases. They are like sodium hydroxide, potassium hydroxide, magnesium hydroxide, calcium hydroxide, etc. So when they dissolve in water, they are already ionic compound. There's nothing to dissociate. But they separate in water solution due to dipole ion interaction. We talked about that, dipole ion interaction, to produce solvated sodium ions and hydroxide ion. For example, sodium hydroxide, dissociate in water. Dissociate means dissolve in water, not dissociate. HCl dissociate in water. Sodium hydroxide dissolves in water and produce separated sodium ion and hydroxide ion hydrated with water molecules surrounding them. Not all bases initially contain hydroxide ions. So some bases don't have OH ions. So by reacting with water, some bases produce hydroxide ion. Therefore, they also indirectly affect the pH of the concentration of the OH ion of the solution. For example, ammonia, NH3, it's a base, but don't have OH. But when you put in water, it produces hydroxide ion and ammonium ion. So it's in a way similar to HCl. Ammonia molecule breaks one of the OH bonds in water and produce ammonium ion and OH ion, hydroxide ion, which eventually gets hydrated in water solution, producing more OH ions in the solution than the amount of OH you had before adding ammonia, therefore increase hydroxide ion concentration. We use curved arrows to show the transfer of proton from water to ammonia similarly. The first arrow shows the formation of NH bond. The second arrow shows the breaking up of the bond. Similar to HCl, reaction between water and HCl. You can write down how the ammonium ion and the hydroxide ion is formed using curved arrow in the reaction. Now, we're going to talk about acid-base strength. One that reacts completely with water is called strong acid. There are certain acids which completely break down, like HCl, nitric acid. We're going to talk about a list of strong acids. They break down completely in water, therefore produce highest amount of hydronium ion in the water solution, depending on the concentration. Strong bases are also completely react with water to form OH ions. We're going to look into what are the strong bases. Table gives the strong acid and bases in this list. Acids are found on the right side, strong acid. On the left side, on the right side, bases are found. On the right side, acids are found. HCl, hydrochloric acid. That's I missing. Hydrochloric acid, hydrochloric, RIC. HBr, hydrobromic, hydroadic, nitric acid, sulfuric acid, perchloric acid. There are 6 strong acids. Can you remember them? HCl, HBr, HI, HNO3, H2SO4, HClO4, perchloric acid. There are 6 bases, strong bases, considered strong bases. Lithium hydroxide, sodium hydroxide, KOH, barium hydroxide, calcium hydroxide, strontium hydroxide. First 3 are group 1A. The last 3 are group 2A in the periodic table. Therefore, it's easy to remember. Lithium, sodium, potassium, barium, calcium, strontium. So if I ask you, which is a strong acid? If you find any of the acid in this formula, this table, they are strong acid. If I say acetic acid, is it a strong acid? No, because it's not on the list. Therefore, it should be weak. Similarly, same idea can be applied to strong acids and bases. So that's how you identify strong acid and bases compared to the list, 6 of them acids and six of bases. If they are one of them, they are strong. If they are not found on the list, that's a weak acid or base. So this strong acid-base strength depends on the dissociation of particular acid in order to produce hydronium ion. We talked about HCl that completely break up, dissociate into hydronium ion and chloride ion. We're going to look into a weak acid case, acetic acid, that when you dissolve in water, only 4 out of 1,000 molecules are converted to acetate ion. Therefore, only partially dissociate in water. So if you look at that reaction, acetic acid plus water produce acetate ion, and just like in HCl, HCl produce chloride ion, acetic acid produce acetate ion. So this arrows between reactants and products are showing equilibrium. Therefore, partial dissociation results from equilibrium acid-base dissociation. Strong acid, the forward reaction is so large, there's no backward reaction almost. Therefore, everything is dissociated into hydronium ion. But when you have a weak acid, when it reacts with water, forward reaction goes towards the acetate ion and hydronium ion, then slows down, and then the backward reaction kick in. This is a equilibrium reactions we talked about in chapter 7. This equilibrium is product favored, reactant favored. Why? Reactant favored means that arrow between reactants and products are more larger towards the reactants. So there's only few hydronium ions are present in the dissociation equilibrium. Weak acid. In the case of weak acid, we take ammonia with water. In this case also, ammonia doesn't completely break the water into hydroxide ions and produce ammonia ions completely. This is an equilibrium reaction again. It's reactant favored. Again, there's more ammonia and water in the medium, in the equilibrium, in the solution, than ammonia ion and hydroxide ion. Therefore, only small amount of OH is produced. Therefore, they are weak acids or bases. In this case, we talked about both weak acids and weak bases. They involve in dissociation equilibria, which are mostly product favored, reactant favored. Reactants means weak acid, weak base are favored in the more concentration in the equilibrium reactions. Now we begin to understand hydroxy acids and hydrogen ion concentration. Acid increase the hydronium ion concentration according to Arrhenius definition. Bases increase the hydroxide ion concentration. Now we have to come up with another acid-base definition, which we call Bronsted-Lowry acid-base acids and bases. In this case, bases don't have OHs. Hydroxy bases are not only the ones that define bases. There are some other bases without hydroxide ions. For example, ammonia. So in that case, we have to focus on proton transfer between acids and bases. Acid donates protons, base accept protons. Let's look at this. These are called Bronsted-Lowry acid bases. Their definition is little different from Arrhenius acid-base definition. A proton transfer reaction takes place in Bronsted-Lowry acids and bases. Conjugate acid-base pair. Any pair of molecule or ion that can be interconverted by transfer per proton. Let's look at these ideas. Bronsted-Lowry definition do not require water as a reactant. So you don't need to involve water. For example, ammonia can directly react with HCl. Therefore, regardless of water, presence of absence of water, absence of water also can describe the ammonia as a base. For example, if you look at this slide, acetic acid and ammonia, which are both weak bases, when they react with each other, they produce acetate ion. Proton is removed from acetic acid, that CH3COOH, that H at the right side, right end, get broken. The proton get broken, then react with ammonia, produce ammonium ion. Then the acetate ion is formed. So this is a Bronsted-Lowry where there's no OH involved. Bronsted-Lowry type acid-base reaction. Acid, in this case, acetic acid, the proton donor, ammonia is the proton acceptor. The acid produce acetate ion, and ammonia produce ammonium ions. Now this conjugate acid-base idea, let's look at it, how we describe that. For the forward reaction, acid-base is acetic acid and ammonia. Once the acetate ion form and ammonium ion form, backward reaction take place. In that case, acid is ammonium ion. Acetate ion is the base in the backward reaction going towards reactant. Therefore, there are 4 acid bases involved in the total reaction. Acid found on the reactant side called acid and base. Acid found on the right side is called the conjugate acid of ammonia. Ammonia is producing ammonium ion. Ammonia is a base. Then base produces a conjugate acid. Ammonium ion is a base. So ammonium ion is an acid, proton donor. So whatever acid found on the right side is called conjugate acid of ammonia. Whatever acetate ion found on the product side is a conjugate base of acetic acid. So conjugate base pair, the difference between acetic acid and acetate ion is a proton. Between ammonia and ammonium ion is a proton. Conjugate bases are related by a proton. So therefore, it's easy to identify conjugate acid-base pairs. If I ask the question, what is the acid conjugate base pair? Conjugate base pair of this reaction, that's acetic acid and the acetate ion. What is the base conjugate acid of ammonia? Conjugate acid pair, ammonia and the NH4. Therefore, you can answer so many questions with this idea about Bronsted-Lowry definition of equilibrium, acid-base equilibrium. So now we're going to look more into Bronsted-Lowry acid-base reaction. When you use curve arrows to show the transfer of a proton from acetic acid to ammonia, we can show again how the proton is broken in acetic acid. So acetic acid is on the right side. It's a proton donor. Electron pair is given to OH. OH electron pair is shifted to the oxygen in the acetate ion. Hydrogen or proton broke up, and proton get attracted to lone pair of electrons on the ammonia. So that's how you explain Bronsted-Lowry acid-base, acid conjugate base, conjugate acid pairs. Now there's an important idea about acid conjugated bases. If you look at this reaction, the acid strength are given, total acid strength of different acids are given. If you look at HCl, remember 6, 1, 2, 3, 4, 5, 6, up to sulfuric acid. No, not hydronium ion. There are 4 here, HCl, hydrobromic acid is not there. So this is not a complete 6 strong acid in here. But the ones on the top from that list on the previous table, hydronium ion is acid. But other acids are, after hydronium ion, other weak acids are conjugate bases. Let me get back. So we look at conjugate bases. For example, ammonia is there. It's not the strongest acid, conjugate acid. Water is stronger conjugate acid. Hydrogen sulfate is stronger conjugate acid than ammonia. Ammonium ion, and as you go down, has other bicarbonate ion, dihydrogen phosphate ion, water, and methanol. So you can see stronger the acid, weaker the conjugate base. Then when you look at the bases, now you have bases here, ammonia. They are mainly not Arrhenius bases. Arrhenius bases are OH ions. Basically, it's OH for Arrhenian acids, Arrhenian bases. So conjugate bases, strong acids have, weak acids have strong conjugated bases. This is the idea. Strong acid have weak conjugate bases. Weak bases have strong conjugate acid. So these are conjugate acids. Okay, we're going to visit this idea again later. Let's worry about it right now. The thing I want you to remember is strong acid have weak conjugate bases. Weak bases have strong conjugate acids. Ammonia is a weak base. Ammonium ion is a strong conjugate base. So keep that in mind. So an acid can be positively charged, neutral, or negatively charged. For example, water is acid, hydronium ion. In water is acid. It's a proton donor. Carbonic acid is neutral. And dihydrogen phosphate ion is a negatively charged species. Therefore, acid could be neutral, positively charged, or negatively charged. Base can be negatively charged or neutral. For example, OH is negatively charged. Chloride is negatively. Chloride is a conjugate base of a HCl. Ammonia is a base. Therefore, base are normally negative charge only or neutral charge. Acids are classified as monoprotic, diprotic, triprotic. There's another definition about number of protons, description of acids and bases right now. Okay, we are talking about conjugate bases, conjugate acid, and charge on them, and we are also talking about how many acidic protons on the acid and base. HCl is called monoprotic. Why? HCl has only one proton that comes out when it breaks up. Hydronium carbonic acid, H2CO3 is a carbonic acid. When you dissolve water, carbon dioxide in water, you get carbonic acid. It has two acidic protons, it's diprotic. Phosphoric acid, H3PO4, is triprotic. Normally, number of acidic protons are written on the right side. Acetic acid is monoprotic. Let's not talk about acetic acid right now. Bronzite Lowry acid bases examples. Carbonic acid, for example, can give up one proton to become bicarbonate ion, then second proton to become carbonate ion. So normally, the first equilibrium is the predominant one. As you go to the second one, bicarbonate formed by removing one proton. The second one is equilibrium is even weaker. Therefore, in a solution of carbon dioxide with water, mainly bicarbonate ion are present. Only very little carbonate ion are present because they involve two equilibrium reactions. First one is even 4%, second one is even less than 0.001, therefore only small amount of second equilibrium participate. Therefore, by carbon dioxide dissolved in water mainly have bicarbonate ion, not like HCl. HCl dissociate completely, only very little bicarbonate. Several molecules and ion can function as either an acid or base. Bicarbonate ion, for example, can give up proton to carbonate, or it can accept the proton to become. So bicarbonate can go either way, act as acid or base. You see that. A substance that can act as either acid or base is called MP protein. So therefore, if you have an example as MP protein ion compound is a bicarbonate ion. Hydrogen carbonate phosphate ion also can be. One of the most important amphiprotic substance is water. Water is amphiprotic. It can accept proton, become hydronium ion, or lose a proton, become hydroxide. So bicarbonate, water are amphiprotic. Proton can be acid or a base, act as a substance cannot be Bronsted-Lowry acid unless it contains a hydrogen atom. But not all hydrogen atom is in most compound can be given up. So to become a Bronsted-Lowry proton acceptor, proton donor, acid has to have a hydrogen atom that can be broken down. But not all hydrogens are broken up in acids. Acetic acid, for example, give only one proton. That's what I was talking about. Acetic acid, that right side hydrogen at the end is the only acid. That CH3 group, carbon is an organic CH bond. The CH in the CH3 group are not broken into proton. Only hydrogen in the carboxylic acid, COOH called carboxylic acid group, only broken down into one proton. Therefore, one proton is produced when acetic acid behaves as an acid. There's an inverse relation between strength of the acid and the strength of the conjugate base. That's what I was trying to explain on that table. The stronger the acid, weaker is the conjugate base. HCl, conjugate base chloride. Conjugate HCl is a strong acid, therefore chloride is weak conjugate base. For example, table 8.2, we look into that. Iodine is a weak base in the table. Hydrogen iodide is a strong acid. Therefore, its conjugate base iodine is weaker. That's the weakest among all conjugate bases. Acetic acid is a stronger acid than bicarbonic acid. Conversely, acetate ion is a weaker base than bicarbonate ion. So, stronger the acid, weaker the conjugate base. So that conjugate base of acetic acid is acetate ion, is weaker. Weaker acid compared to bicarbonic acid is weaker compared to acetic acid. Therefore, bicarbonate ion is stronger than acetate ion. Stronger conjugate base. So we talked about, I'm going to start from acid-base equilibrium slide where I left off last time before the internet went out. We know that HCl is a, can you guys hear me? Are you guys there?
Yes.
Okay, I'm glad. There was some problem with the internet. We know that HCl is a strong acid. Now we're going to look at the acid-base equilibrium in detail, which means that position of this equilibrium lies very far to the right. That is a complete reaction. There's no equilibrium. Therefore, equilibrium constant is 0. Equilibrium constant is very large, not 0. Product concentration is higher. Therefore, equilibrium constant is very large. Very large means it's product favored. In contrast, acidic is a weak acid. The position of equilibrium is tilted towards the reactant side, left side. Therefore, equilibrium constant is smaller than 1. Smaller than 1 means reactant favored. But what if this base is not water? How can we determine which are the major species present? For example, Bronsted-Lowry equilibrium reaction between acetic acid and ammonia. So that's the question. How you determine which major species present. We can write up an equilibrium expression for this also. To predict the position of acid-base equilibrium such as this, the last one, we do the following. Identify the two acids in equilibrium, one in the left and one on the right, using the information in table 8.2, which is the strong acid and which is the weak acid, and determine which stronger base and which is the weaker base. So then you transfer the proton accordingly. The stronger acid reacts with the stronger base to give weak acid and weaker base in the equilibrium. For example, if you look at the table, ammonia is a weaker base, weak acid. Acetic acid is stronger. So therefore, reaction goes proton transfer from acetic acid to ammonium ion, ammonia to produce ammonium ion. So that's shown here. Base goes to ammonia, goes to ammonium ion. And that's the blue is the conjugate base acid conjugate base conjugate acid pair. Red one is acid to okay, that's where we stop. Let me see whether they allow me to. Okay, we talk about acetic acid and ammonia reaction. How we identify the reaction based on relative strength of acetic acid and ammonia. So ammonia is a stronger base than acetic acid. Acetic acid is stronger base than ammonia. Therefore, acetic acid become the acid and the ammonia become the base in the reaction to produce acetate ion and ammonium ion. So these conjugate acid-base pairs are shown in red and the blue. This equilibrium is more towards reactants or the right side because of the acid and base both are weak. So therefore, equilibrium is position of the equilibrium lies to the right. I'm sorry, on the side of the weak acid and weaker base. So weaker base are acetate ion and ammonium ion. So it lies to the, when you start with stronger acid and a base, they go to weaker acid and a base. So therefore, for weak acid base equilibria, it lies most to the right. Let's see one more example. Predict the position of equilibrium in this acid and base reaction. Locate the strong acid and strong base on each side of the equilibrium. Carbonic acid is a strong acid than the OH. Therefore, these are again in equilibria. Right side is the favored. Strong base, strong acid goes to weaker base and weak acid. Weak acid, weaker base side is stronger. Equilibrium lies towards right side in this case. When a weak acid dissolves in water, we can write down acid dissociation constant. For example, for this equilibrium constant could be written. K is product concentration raised to the stoichiometric coefficient power of stoichiometric coefficient. We talked about that in chapter 7, how to write an equilibrium constant. So for acid dissociation equilibrium, K sub A, it is HK is the reactant. Water is a liquid. This is a pure liquid. It disappears. I talked about when writing equilibrium constants, pure liquids are removed from the equilibrium. Pure solid and pure liquid. Water is a liquid, pure liquid, therefore removed. K sub A value for this weak acid is concentration of A negative ions, concentration of hydronium ions divided by concentration of HK. Another example, K sub A for acetic acid is, that's a real example, 1.8 10 to the negative 5. If you look at the K sub A value, it's very small. That means only few molecules of acetic acid is dissociating in water. Because the ionization constant for weak acid are numbers with negative exponent, we commonly express the acid strength as pKa value. K sub A value is 1.8 10 to the negative 5. How do you get the pK value? You take the log of 1.8 10 to the negative 5 and change the sign, you get the pK value. So if you plug in your 1.8 negative 5, take the log of that value and change the sign, you get 4.75. Please do it on your calculator. Enter 1.8 10 to the negative 5 and hit the log button. And on the answer, change the sign, you get 4.75. So 4.75 is a mathematically easy to deal than 1.8 10 to the negative 5. So we use to indicate acid strength K sub A value or pKa value. Values of K sub A or pKa for weak acids are given in the table 8.3. As you study the entries in the table, note the inverse relationship between K sub A value and pK value. This is important to notice. The weaker the acid, smaller the K sub A value, but larger the pK value. So if I give you a list of K sub A values for weak acids, the strong acid has large K sub A value, but inverse relationship. K sub A is larger for strong acid, but the pK value is smaller. For weak acid, K sub A is smaller, but the pK value is larger. Let's see this relationship. Phosphoric acid. K sub A value is 7.5 10 to the negative 3. So on the K sub A value increases from bottom to top because 10 to the negative 3 is smaller number. Therefore, stronger acids are on the top. Now, pK value is largest for the smallest K sub A value. For example, hydrogen phosphate ion at the bottom, 2.2, 10 to the negative 3, 13, has the smallest K sub A value, but it has the largest pK value. So when you compare in K sub A values, larger the pK value, stronger the acid. When you're comparing pK values of different acids, smaller the pK value, weaker the acid. So therefore, you have to know that there's an inverse relationship. We talk about this. Weaker the acid, smaller the K sub A value, but larger the pK value it is. Now we're going to look at properties of acids and bases. Acid and bases reacted with each other in a process called neutralization. These reactions are discussed in 8.6. Reaction with metals. Metals also react with acids. Strong acid react with certain metals called active metals to produce salts and hydrogen gas. These are redox reactions. Metals go into solution, releasing hydrogen from the acid, producing salts, metal salts. These are single displacement reactions. For example, magnesium solid metal react with HCl. HCl is a strong acid. So when you compare acid reactions with active metals, you can see a activity series. Certain metals react faster with a strong acid. Therefore, a series of metals are arranged according to their reaction to a strong acid. Reaction with metal is a redox reaction. single displacement reaction. The metal is oxidized to metal ion. Hydrogen proton is reduced. Proton in the strong acid is reduced to hydrogen according to the equation. This is a redox reaction. 2 electrons are transferred. Therefore, acid-base reaction with metal is neutralization, is acid-base reaction. Reaction with metals produce activity series for metals in their reaction with strong acids. The activity series is given here. When you compare the redox reaction, strong acid with metal is a redox reaction. If you compare the half reaction, oxidation half reaction here, this is a series strongly reducing lithium, potassium, calcium, sodium, aluminum, manganese, zinc, chromium, iron, cadmium, nickel, lead. Now, when you come to after lead, you see hydrogen going to hydrogen plus. So after hydrogen, metals below hydrogen are not active. These metals do not react with. So therefore, metal reactions with strong acids indicate the reactivity of certain metals in their replacing hydrogen ion from strong acids. So they are related to redox reactions. We talked in the previous chapter, energy storage. Okay. Properties of acid-base reaction. This is neutralization reactions. We talked about metal reacting with strong acid, giving the activity series. Now we're going to look into reaction of metal hydroxide and acids. A reaction of acid with metal hydroxide gives salt plus water, HCl with KOH, produce water and KCl. Salt is the KCl. So this is how you can neutralize an acid or a base, either using acid on base or base on water, on acid to neutralize, producing water and salt. The reaction is more accurately written as follows. Net ionic equation. This is the ionic equation. If you look at this reaction, you break up HCl into hydronium ion and chloride ion. KOH, all the AQ formulas with AQ could be broken down. L cannot be broken down because this is not broken down. Water is there. Therefore, chloride and potassium are spectate ions. We talked about that in previous chapters. Omitting spectate ions, chloride and potassium from right and the left side produce acid-base neutralization of ions, acid and bases are simply a neutralization of hydronium ion with hydroxide ions, producing water. Reaction with metal oxide